Garth is a recipient of the 2005 J.W. Graham Medal in Computing and Innovation. He received his BMAT from the US Waterloo in 1983 and his master's and PhD from UC Berkeley in 1987 and 1991, respectively. He is currently an associate professor at Carnegie Mellon, as well as the founder and co-founder and chief technology officer at Panasas. So we have all three logos on the slide. Panasas, Waterloo, and that's president of the Carnegie Mellon. Garth will be awarded the Graham Medal tomorrow for bringing together academic excellence with entrepreneurship in a tradition set by J.W. Graham. He was also awarded the 1999 IEEE Reynold B. Johnson Information Storage Award for outstanding contributions to the field of information storage. Garth is probably best known or very well known for his work on RAID, and I wanted to characterize that for just a minute. Garth's thesis in RAID is probably the gold standard to which you can hold any system's thesis to. It has three qualities which are amazing. One is simplicity, depth, and impact. In terms of simplicity, the RAID idea is something you can explain to your grandmother. In terms of depth, it has probably thousands of people earning full-time salaries for working on it now. And in terms of impact, it is the basis of a multi-billion-dollar industry.
About 15 billion.
About 15 billion. Thank you. In terms of, any thesis that can achieve these three touchstones of simplicity, depth, and impact, I think is well worth emulating. After his groundbreaking work a while back, Garth has gone on to do many other things, including most recently virtual object storage, and we'll talk about today. Okay. Let's give him a warm welcome.
All right, so I'm going to take a more or less a chronological walk through my work with storage technology through to the later results that are impacting the world now, and how I took that a commercial approach to driving that forward. So this is a path. It starts with my experience in RAID and takes us right up to the current day. So let's just pop up a level. Information storage, particularly hard disks, are growing at phenomenal rates, and they're being driven by our needs for them, our desire to use large amounts of information. That can be characterized in at least three broad ways. The way that most of us are probably familiar with is these things, right? This is an iPod, and an iPod made a really big change in the way people interacted with music because of what? Because of a 5 gigabyte hard drive that fit inside it. Prior to that, you had an hour of music that you could carry around with you, which we did, and Walkmans had a big impact on us. But this guy carries 4 days of music on it and about 4,000 pictures, right? And that is the high density, low cost of magnetic technology. Magnetic technology is very cool. We don't get to look at it very much, but inside this thing is a disk drive. That disk drive has a density of information that is higher than the DRAM density. So we're packing things in very small spaces. It's spinning with a magnetic head flying micro inches off the surface of that disk. It's turned off right now, so it's not relevant. But which means that it's not actually flying. It's sort of swimming in the surface that is slightly porous on the edge of the disk. And then that whole thing has to be seen as magnetic flux transversals, which will cause a current to flow. That has to be picked up, and an analog digital system that has to go at speeds of 500 megabits per second to convert that to information. That type of technology is now down in the $50 range, and it's providing huge amounts of capabilities. Here, it's about convenience for us, high fidelity in information. Here, it's about entertainment. And this industry is amazing. This industry sets a standard of improving the quality of the realism that you get to watch on the movie screen every given year. To do that, they have to drive their IT, the capability of computing and storing information at phenomenal rates year over year. Movie to movie, they have to improve it. And so these guys have a huge demand for information. For example, the texture of something like a surface, well, the fish one's easy, but think of Shrek's fur type surface. That information typically takes between about a 10 megabyte to a gigabyte map of the texture so that you can map fur onto the surface of a being. So every single frame of the 24 frames per second is maybe 5 or 6 characters in that frame. There is a large texture map for each one of them. There is a polygon structure to describe them. The rendering process is to pull down the polygon, pull down all the texture maps, figure out the positions, map the texture maps, and map all the light effects onto that frame, and then do it again. Okay, and this standard is driving a whole industry of computing, high-performance computing for entertainment. Out here, if you look at the science world, physical simulation, or simulation of physical processes, is why we can find oil at better prices. It is why we can build airplanes with better airflow and cars with better airflow, better mileage. And physical processes, and it's why we don't have to explode nuclear bombs to know that they're in good shape, because we simulate the whole process. Those simulations run weeks to months to years of simulations in order to map the physical behavior of individual atoms and molecules and different structures that are being simulated down to great detail. Those types of things require huge computing resources and require huge storage resources. And this is a range of the kinds of companies that drive this. So it is, in fact, the interest of people and of the industries serving people to process information at greater and greater fidelities that is driving this industry. Okay. So let's talk a little bit about those trends. 1992, I had just finished my dissertation, and at that time I had a pretty good handle on what was available in the technology. 2002, the guys at the Mass Storage Symposium asked me to do a 10-year retrospective and perspective on where we were going. So I went through a projection of 2012. Now, these projections are just the simple, nothing super intelligent, just compare the current in 1992 to the current in 2002. There's a ratio there, and extrapolate forward. But this is saying the capacity of a 3.5-inch disk that you have in your hand that was 320 megabytes in 1992 became about 100 gigabytes in 2002. It's now pushing 400 gigabytes, which is the factor of 4 in 3 years. So I think there's every reason to believe we're still going to be on the curve for having 30 terabytes in a 3.5-inch disk. 30 terabytes is today what a supercomputer calls the storage system, 30 terabytes, one ARM. In dollars per byte, it's been even more impressive. I think that this projection isn't going to work. But roughly, in 1992, it cost $600, $600, $700 for that disk. And that would be $2 a megabyte. A couple years ago, it was down to $2 a gigabyte. It's down to about 50 cents a gigabyte now, factor of 4 again. I don't think it's going to make it down to $2 a terabyte in 2012. The reason is that we were on a bubble of 100% per year increase in capacity in the late 90s, and we won't be able to stay there. It looks like we're going to about 50% per year for the next 5 years anyway. So maybe it's $20 a terabyte in 2012. The amount of information on a single track, which is the most efficient unit to move in a disk, went from 32K to 330K, and it's going to be 3.5 meg. The way to think about that is if you're building an application, you want to use efficient storage, the unit that you need to move is going up a factor of 10 in 10 years. Right? Or you are just going to be less efficient. This is the most interesting characteristic about storage, that the average access time to fetch a random piece of information from a disk is going down at only a factor of 2 every 10 years. So that the most critical resource, that is to changing what is sequential, moving from one place to another, is going to be only harder. The interfaces, it used to be that disk interfaces were much faster than network interfaces. Well, it's not the case anymore. Network interfaces are about the same speed now, coming out of any box going to the outside world as compared to going to the disks. And the InfiniBand guys are already plotting the 40 gigabit per second and talking about the 160 gigabit per second interfaces coming out. Disks won't do that. There's no particular reason for disks to do that because this rate of growth is not that fast. So you only have to get data off to satisfy the individual disk speed. Here's an interesting number. Well, I'm sorry. This is the bandwidth. Roughly, bandwidth is going to be how much data there is on a track versus the time it takes to rotate around. That number is going up at pretty good rates, not as fast as the overall density. So then what you do is you take the total density divided by the megabytes per second, and you get the read once. Let's call that the temperature of the information. That is, if you want to visit all the information on that drive once, then 10 years ago you could get it in 3 minutes. But in a few years, it's going to take half a day just to visit all the information just once. Right? The way you think about that is that the temperature of each individual byte is getting lower, the amount of work you can do with it all the time. And what that means to us is that you're classifying your data, and that you probably have hot data, the same hot data on some of the disks. It's consuming most of the resources of the disk, and you're filling the disk up with stuff you don't use, either because you're not deleting it or because you're using it less frequently, but when you do use it, you get benefit from it. If you switch to the arrays, the entire boxes, what you'll see is not quite as a factor of 1,000 growth in the total capacity. In fact, better than 1,000 because we're putting more boxes in. And actuators, the number of arms are going up at phenomenal rates. IOs per second, this is the critical limiting factor, is not going up as fast. Total bandwidth can go up as long as we use all this parallelism, so we can fight the coldness of individual disk bandwidth with the speed throughout the entire array. So as long as you can fetch everything at the same time, you can fight the performance. The reason here is that there was architecturally bottlenecks, and I'll come back to those bottlenecks in here, but we can get somewhere out of there. I want to throw this up in part because it's a snapshot of a projection in technology trends, and there are huge numbers in 10 years of changes that I wanted you to see. All right. Now I want to pop up a level. I've told you a little bit about the industries and the use of that storage. What's happening there is the lower cost IT, lower cost, the ability to perform computations and storage cost effectively, is driving down so quickly that it opens up opportunities. Well, how is that happening? We used to build computers as monolithic supercomputers. If you happen to work for Los Alamos National Labs in the 1970s, and you wanted to build a computing application for science, government science, you wrote a spec for a computer, and you dictated everything, and you'd find multiple companies that would be happy to build that computer specifically for you because the ratio of the total amount of money spent by the government on computing was large compared to the total amount that people spent on computing. Okay? That's gone, right? Right now, people are the ones that are supporting the computing industry. Governments have tiny amounts of money compared. Universities have tiny amounts of money compared to what people spend on computing. Which is why today, if you talk to a designer about planning their next generation of computers, they're asking, what will the chip be in the PlayStation? Because if I can use the chip in the PlayStation, I can probably use the chip with the highest rate of technology improvement. Right? And until recently, that was looking like it might have been the Motorola PowerPC class chip, and that led to the speculation in the cell processors that IBM is pushing. It's going into things like blue gene technology. That's where they've been pushing. But it's not so clear that that's going to happen. But that's what we have to watch. And you can talk to the ATI, Nvidia folks, and they will tell you that the cheapest computation is inside the graphics processor, and that the combination of their efficient computation and entertainment technology means that they have a chance of being the processors of the future. But right now, it still looks a bit like Intel. What happens is that a component in a cluster is what I would call the sweet spot. That is, its architecture is ancient. It's the IBM PC architecture. It has huge volumes. They're manufacturing these things, exactly the same chips, exactly the same boards for right across the PC industry. So the cost effectiveness, because of volume, is very, very, very good. Then you put together a bunch of those things, and you get the computational power that is substantially the same as the traditional supercomputer. Now, unfortunately, there are certain applications where that's not true. And so there's still some of these that are built for those applications. Although mostly what's happening is those applications are working very hard to try and use this type of an infrastructure. Those applications tend to be shared memory, where every processor is touching all memory sort of at random in rapid succession. Most of the cost of trying to provide solutions there is driven into high-performance networking. That's this part. Okay, so we've replaced these expensive subsystems with these less expensive subsystems. We get a great improvement in price performance. We have a lot of networking bandwidth. So the question I would ask is, well, what happens to the rest of your technology? Typically, in the data center, 40% of your cost is down here in storage. Right? And the networking plus compute is no more than 60% of your cost in IT. So if you drop the price performance of this by an order of magnitude or two, which is what we're looking at, and you don't do anything about the price performance with this, then if you maintain that same cost balance, you have lousy price performance in the storage subsystem. And if you don't, then you have cost moving out of this part of the system, which is where everybody wants their cost because their computing cycles is what matters to them, and down into here. So what has to happen is a price performance shift has to occur here to balance the price performance shift. And so that's essentially a big picture of what I've been doing over the last couple of decades, is to work on the price performance of the architecture of storage that would lend itself to that price performance shift. Broadly, I say that the answer is you build storage with the same architectural approaches that you build computing. That is, you must build them out of sweet spot components. You have to build them with scalable networks. And you have to have a lot of parallelism that goes on between the two subsystems. Then you can get dramatic increases in bandwidth. Now, the core reason for that is that disks themselves have lots of bandwidth. In order to put a disk into a system, you put it behind a controller, and then you plug the controller into the subsystem. The controller's overhead cost. Right? If you match the disk resources, the bandwidth out of the disk, to the controller, then you have way too much cost in the controller. The dollars per gigabyte, which is still the dominant reason the way they buy storage technology, will be too high. So people roll more disks in behind the controllers. Well, now the effective bandwidth you can push through is a small fraction of the disk's resources. In fact, it's about 10%. Right? So at least an order of magnitude of bandwidth is lost by that architecture. What we've been doing here, and I'll talk more about this, is to break open the devices, get them out from behind the system, put them on the network themselves. Okay. Another key thing. People cost more than computers. People cost more next year than computers as a ratio as well. The ratio of what you're spending on people is going, relative to computing, is going up. Well, that's the wrong direction. One of the key problems here is that's one computer, or maybe a couple. That's 1,000 computers. Managing 1,000 computers by people is much more difficult than managing a couple computers. Right? So the capital costs drive you in this direction, but the operating costs drive you in that direction. Right? So what they've had to do, and we're really only about halfway through this process, is we have to develop tools that make this thing look like one computer to its administrators and its users. And that's awkward. There's 1,000 fault domains instead of a small number. There's 1,000 OSs that can be misconfigured. There's 1,000 user spools that can overfill. There's all these problems that we have to move out of the way. Okay. Now, that's the high-level story of my sort of thrust of work in the last couple of decades. Build storage architectures that allow us to evolve storage at the rate that we evolve the computing infrastructure. All right. Now let's go through a little bit of the detail. So yes, RAID is the thing that I probably talk about most over the last few decades. And you know, when I did it, it didn't seem like it was a very big idea. Prabhakar, you were there. You know, it didn't seem like it was a huge leap forward. But what we did was we provided an organizing principle for how you were going to handle storage. And that organizing principle enabled a lot of people to jump in with the problems they had at hand, figure out how they were going to solve their problems in the context of multiple disks. Let me go back to how it happened. In the 80s, what you had as the dominant architecture was IBM. So today we all hate Microsoft. Well, in the 80s we all hated IBM because it had undue control and influence over what we used. And when I was here, there was a big IBM. Is there? That's long gone, right? Yeah. But it was the big computer. And the VAX off in the corner was the little computer we all loved. Right? Its architecture was a big CPU. It had another computer called the channel that was a computer devoted to moving storage bandwidth. That thing was a washing machine in size. They had another computer down here that was the controller. It's another washing machine in size. What this thing did was convert analog signals to digital signals to feed the channel. And then the disks themselves were washing machines in size, and all of the electronics to process them was essentially off board. An analog signal came out and ran along those wires. Right? What happened, the big thing was, we pushed VLSI. And by pushing VLSI, we drove the cost of this functionality down by integrating all of that functionality into a small number of chips. So we went in the era of SCSI and put a little controller that combined these two functionalities into an ASIC and a little microprocessor on the back of a drive. That was the SCSI revolution, happened in about the early 80s. And it meant that every individual disk could stand alone and provide most of this functionality. And you could pump them out in volumes for the PC industry starting in the early 80s, so that these things were cost effective. So, mid 80s, I'm working on a shared memory parallel processing application, and everybody and their brother is working on shared memory multiprocessors, and we're trying to find a sort of fresh domain where there's open problems. And what we said is, there is some kind of a transition going on in here. Let's go have a look at what it is. What it meant was we could build computers differently, storage for computers differently. And what we did is we built them around SCSI. We said, let's take the space of that washing machine and replace it with 100 3.5-inch drives. Each one of those 3.5-inch drives is individually smaller, slower, but they were also less expensive. Put them together, I had something that was cost effective. I had something that had more raw capacity, more raw bandwidth, and more parallelism, so higher performance. That was the key idea. Then, it took like about 15 seconds for someone to say, and you've got 100 fault domains instead of 2. Well, all right. That means that I got to do something about the fault domains, and that led us into redundancy. That is some kind of an encoding so that you can tolerate single failures. Disks are nice things in that when they fail, they stop talking to you, so you know they're failed. And that's different than communications and transmissions on a wire. So they talk about error correcting codes for transmissions on a wire and erasure correcting codes for disks, as you know they're missing. So these erasure correcting codes said that a single error tolerant code, Parity, can be a single erasure correcting code. So maintaining a single Parity disk across this row of disks allows us to recover from a single fault. So we said, all right, we're going to introduce redundancy. We're going to do it by either mirroring complete copies or by this Parity approach. So this is a picture. This is the Parity approach. This is a disk. Here's an individual block. You can have a mirrored pair for the 0 block, and then you can have a mirrored pair for the 1 block. The alternative is that you have 4 disks, and you have 3 data, and then you calculate the parity, and you store it off on the endpoint. Right? What's the trade-off? Well, this one has a much lower capacity overhead for redundancy information, like 25% or 33% in this case versus 50%, 100% in that case. The other difference is that when you do writing to this thing in small amounts of data, you can simply write twice in 2 different places. But over here, if you write only 1 block in there, you have to recompute the impact on this code, which requires at least either reading the remaining blocks or noticing what bits changed in here and change the corresponding bits there. So it's harder to do small random updates in this RAID 5 approach, the 5th level, and it's much less expensive, and therefore a higher bandwidth in writes as well. So this trade-off continues today, and this industry, the external disk array industry, which is about a $15 billion industry, is based on offering this basic trade-off and then a whole lot more that they've added to it. This equation down here is the basic mean time until data loss, which, of course, I don't care about the mean time to data loss because the numbers are hundreds of years. What I care about is that the exponential lifetime model, or the Poisson process for failures, is a good model for disk failures. And in that case, the probability of data loss in a month is directly proportional to 1 over the mean time to failure. So if I can double this, I can cut in half the probability of data loss in a month. That's useful to me, right? These equations roughly say that I can square the mean time to failure of the individual disk. That's the big number. That's the good thing. And then under here, here's the prices I'm paying. This is the mean time to repair. This is like the group size. This would be 4. This would be 2. And this is the total number of disks in the environment. So roughly, the prices I'm paying as I get this improved mean time to data loss is how long does it take to repair after a failure? What's my organizing unit? 2 versus 5 or whatever, 4. And what's the total amount in the system? That trade-off is still here. I'm going to come back to that trade-off because of a recent innovation in that area. Now, this is, it's kind of as deep as I'm going to go into some specific graphs from a simulation study from a paper done in 1993. My main point on this slide is to talk about concrete versus virtual. There's a lot of buzzwords about virtual. But virtualization as a technology is about abstraction. What usually happens, and it happened to us too, is that when you do something new, it's so bizarre, people don't really follow it. They want to see an example. They figure out the example, that's the only thing they remember. The abstraction may or may not stick with them. So when we first did RAID, we talked about the XOR of 4 blocks being put into the 3 blocks being put into the 4th block. People walked out doing exactly that. This is physical sector 0 versus physical sector 0. Physical sector 0 is XORed into physical sector 0. Well, that works. That is, in fact, what the example was about. But it's over-constraining the problem. Right? In fact, all we need is distinct fault domains. Right? That as long as I take a unit of information, 1 bit, in one fault domain, XOR it with a unit of information in another fault domain, XOR it with a unit of information in a 3rd fault domain, and store that in a 4th fault domain, then I have single erasure correction properties. Right? So I don't need these things to, in fact, be the first sector in each of the disks. So this project that was done in the early 90s said, well, what if I take this logical array, G wide, with 4, G being 4 blocks in a RAID stripe, and what if I spread that out over 7 disks? What kind of a trade-off do I get? Well, my overhead stays with the 4, but if disk 1 fails here, there is no information lost in this parity stripe, because it's only 4 wide. It's on that one, that one, that one, and that one. So I will not read these S blocks in the reconstruction of this disk. Whereas in this physical instantiation, 1 disk fails, I will read every other sector in the organization. What that allows me to do is to trade width here against the amount of work I have to do in reconstruction. And I can make the repair time, that is, it's a trade-off between this parameter, reconstruction, and this parameter. No, that parameter. No, that's right. I'll get it right. It's actually a trade-off with this parameter right in here. But so this was an early experiment for me to try to virtualize the solution of RAID and say that RAID is just a relationship amongst fault domains and encoding of information. And what these things actually are, they don't have to be disks. They can be disk arrays. They can be other things. And what I'll talk about in a while is how we move that up from the disk abstraction into the file abstraction, and just say that as long as I can assign the pieces of the file into different fault domains, different computers, different servers, whatever you want, I can build RAID solutions layered up very high in the system instead of very low in the system. Okay, now I'm going to break off and take the next trend. So somewhere in the early 90s, it looked, 1991 when I was finishing my dissertation, it didn't look like there was going to be a RAID industry. There were a couple of small startups that had picked up the ideas and kind of branded the names and were trying to use Berkeley professors say this is a good idea, therefore you should buy it as a marketing campaign. It didn't really work, but what was happening was the industry as a whole was seeing the power of it, and they were bubbling up understanding, playing with it in the back lab, trying to find a product they could ship. They did. By about 1994, it's a real industry. Right? But our paper came out in 1988. So that was about a 6-year span. I'd say that's fast. That's fast from an idea organizing an industry until a decent market. I'd say that, in fact, it's more like 8 to 12 years for most ideas. Right. All right, so I decide that it's time to do something else. Well, key thing that's drove a lot of this technology, VLSI. As those guys figure out how to make the masks that litho the surface of a disk smaller and smaller and smaller, cut smaller and smaller lines, they put more transistors onto the back of a drive for the same cost. And that means more computing resources. So how did this happen in the disk world? Well, we started off in the early 70s with this interface called ST506, pure analog. All it did was send an electric signal, a waveform. In the late 70s, we had enough resources to, in the drive, separate those waves, turn them into a digital signal, and separate the clock and data. In the mid-80s, we turned around and said, well, we can put buffering in there and command processing and do store and forward. So mid-90s, I'm finishing up the RAID work, and Fibre channel comes out. So Fibre channel seems to be just another SCSI interconnect. But there's a funny thing about it. SCSI is a ribbon cable protocol. It's a bunch of wires, and if I want to talk to you, I put the voltage up on one wire. You notice the voltage up on that wire, so you take another wire, you raise the voltage on that. That tells me that you're paying attention. So I load up a value on a bunch more wires, then I pull a voltage down on the original wire. You see that go down, so you copy off the values and then put your voltage down, and I have transferred 1 byte. Okay? That thing is back and forth. It means that everything is going to be close in distance. It means we can't have very many ports on it because of all the reflections on, electrically from all of those ports. So it is awkward. Networks, on the other hand, take the information. They say, oh, I want to send it to you. I got an address for you, and I got some kind of a routing information, and here's the data information. And I can put it into a packet, and then I shove it out. Bang, 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 on a wire in a transmission way, so that it goes glancing off by itself. You have to pick it up, notice it, tell me you got it. I get 1 round trip. All right? That allows wires to get a lot longer and a lot faster. Fibre channel is a network doing this to SCSI. So they had packetized SCSI. I looked at Fibre channel. I said, well, why is this, what is this different from Ether? Well, you know what? Not much. The connectors are the same. The cabling is the same. The encoding is the same. The oscillators, one was 2 to the 10th and the other was 10 to the 2 in speed, and 10 to the 3 in speed. So they were almost the same. The protocol layers above were designed by different groups of individuals. They accomplished the same functionality. That was a standard network carrying storage protocols. That said to us, it is very clear that storage can go on any network. That means it will go on any network. So it has, in fact, come out from behind systems. Storage is, these protocols, iSCSI, is a mapping of the SCSI protocol onto TCP/IP onto any network. Right? And so that has happened. The other part about this is the whole interface here evolved over time to be stronger. And here it didn't evolve much, although RAID was interfacing in here. So the question is, what should this interface be that can make storage a first-class citizen on a network? And the question we asked ourselves is, what value proposition do we give the customer if we change the storage interface? And we argued that the most important one, the most valuable one, would be that storage should be able to transfer directly to the compute nodes and not have to go through a file server. Because the file server is like the controller bottleneck I was talking about before. If I push all the data through the file server, it will become a bottleneck. And making it fast enough to go really fast is too expensive. But if I can make these things be able to be connected and owned by this box, but also connected and used by these other boxes, then I can get rid of that architectural bottleneck. And making that possible would be a big step forward. Right. So the architecture we developed at the time, we called it network-attached secure disks. So this is the architecture where storage goes out. Actually, a customer asks for data. What happens? They take a request, they wrap it up in a network protocol, they send it to the file server. The file server goes to the networking layer, tearing off the headers on the request, passes it into the file server itself. It says, get me the data of file foo. This thing takes that and it translates file foo into address bar on the underlying disks. Then it forms packet headers in Fibre channel land, transmits the request for data from address bar in this other namespace into the disk, which pulls it off the surface, wraps it up in Fibre channel headers, sends it back to the to the file server, which tears off those headers, says, oh, here's your bar, that's foo, let's wrap it up in some more headers and send it through. I did that example specifically because you should hear me just saying that the whole functionality of this box on the critical data path is to be a router. It takes data in requests in one namespace, maps them into another, forwards them, and it takes data in that namespace, maps back into the original one, and forwards it. This box, although it does add other functionalities, most of what it's doing, most of what you pay for the computing resources to do, is copy in to out. Let's get rid of that. Routers are good. We know how to build routers. We know how to build switches. Let's just put that into the network. All right? How can I do that? I have to separate the translation step from the copy step. Translation step doesn't have to be done all the time. Let's take the request, send it up to a file manager, and say, in the future, if I want to access file foo, what does it map to? And this guy says, well, I can look at your credentials. You have access. I know what's going on with that thing. Here's the mapping. All right, here's the mapping. It says file foo maps to address bar. Okay? Now, this thing can say, oh, well, I'm going to fetch address bar directly from storage. Okay? That's the basic step of what we did in the network attached secure disk. Now, there's some security protocols and other things in there. Here they are. In fact, it turns out this is going to be the big reason why the protocol change is going to take in the industry. And that is that the fiber channel iSCSI class solutions have no inherent security, period. Their architectural model is that disks are inside the computer. There's nothing there protecting them except the walls of the computer. But disks aren't inside the computer anymore. Disks are outside on the network, and therefore there needs to be something else involved. So here's the basic model. Client asks for access to a file. What they get back is this description, this mapping of that information, and they get back the freedom, the right to access it, and that is a list of arguments. And they get back a key for signing their requests, which is computed from a cryptographic serial number and the rights of access. They then use this to sign their requests such that the underlying device can, from the information sent in and the secret key, do the double signature and prove that the request is fresh. Right? What this means, forget about the crypto part of it, is that it means that the device is verifying every single access as it's happening, right, with relatively strong solutions. And that gives us fine-grained access control at the data level in network storage. And that's what's not in the block model and why this thing's going to happen. Okay. I'm going to do another big break. So that was a project to develop a new interface, right? So a new interface in storage isn't very much use to you. Almost nobody here talks directly to storage, right? What you do is you talk to file systems. You talk to databases. So unless this new interface helps file systems and databases, you're not going to go anywhere. So what's going on in file systems? Well, NFS, which is the only industry standard file system that everybody uses, and CIFS is used by a large number of people, but I wouldn't call it there's a different definition of standard for CIFS versus NFS. It's the monopoly standard. Individual nodes in a cluster that use NFS mount these subtrees. A subtree corresponds to a piece of disk which has a file system on it. And you mount one here, and then you mount another on a leaf node, and you build up a whole tree by mounting these things. Well, what NFS does in its metadata state is that the root of this tree corresponds to a name, the share name or the export name, and one IP address. That one IP address is across the network to a server. So everything you do in one of these triangles is done against a specific machine on the other side. That should look just like the bottleneck I've been talking about, and it is. NFS mandates that all of the work for an NFS mount go through a single machine. Right? So that single machine has some number of disks behind it, and those volumes are mapped into the capacity of those disks. And if you want to try and scale the capacity of one of these triangles up or support more overall work, you'll exceed the capabilities of one of these boxes or the physical disks behind it. When you do that, at the moment, you have no choice but to go in the namespace, and try to divide out. So users A to K are going to be in this volume, and users S to Z are going to be in this other volume. Okay? And so you'll cut the namespace and you'll try copying these things over and moving them to many of these different servers. The problem with that is people time. That is a very awkward, time-intensive thing to do. It's also not transparent. So NFS, while very widely used, does not meet the needs of higher performance solutions. What we're going to get in the next range of products is a very simple forwarding technique. That what we're going to do is, instead of having this drive have a table of different servers, it's going to have just one. And when it gets to this server is going to have what used to be the table there over here. So if you go to your server and you really got the wrong one, it'll forward the request to the other server, which will do the work and send the data back. Now, in some sense, this is an improvement, because if you have a large number of these clients and they all bind to different servers, then you will increase the total CPU power. You can scale the total CPU power available to supporting NFS. Right? Now, you're going to double the amount of work in the data path, but you're still spreading it over many machines. But the total capacity available in any one volume or namespace is fixed. The total bandwidth is fixed because it's going through that server. So this is only a half measure. As a result, a lot of companies have developed something we call a SAN file system or a cluster file system to be more aggressive. This came about because of something Mercury Computer did. Mercury Computer had cluster nodes. They had a CIFS server. They had a Fibre channel back-end, arbitrated loop, which was a ring connecting a bunch of disks. And the clients would go over the LAN, which isn't even shown here, the Ethernet, to request CIFS data, and then it would go fetch through the disks back through the server and back to the clients. Well, those Mercury Computer guys noticed that they could put Fibre channel ports into these clients, and they could listen in on all the traffic. And they could snoop on all the traffic. And, the CIFS server's functionality wasn't changing very fast, so they reverse engineered the functionality. And they basically said, if I sit here and watch commands go by, I can build a partial image of the metadata state for the CIFS server in each one of the clients. So then what I'll do is, when I get a request, instead of forwarding it out, I'll check and see, do I have enough state inside the client to be able to do all the translations and the access control myself? And if I do, I'll just reach and go directly into the storage. Right? Mercury Computer sold that to IBM. It was called Sanergy. IBM sold it for a while, but then everybody else sort of said, we really should be going directly to the storage from these things. So they rebuilt it. It's now SANFS is the storage tank is the new and improved, and threw away the Sanergy and did it again. Meanwhile, EMC did High Road, SGI did CXFS, Sistina did the GFS Global File System, and then sold it to Red Hat, where I think it's still called GFS in Red Hat land. There's a bunch of these things. Now, one of the things that all of these guys have a problem with is this is still Fibre channel. Fibre channel is modeled on the fact that these disks are inside a computer. What that architectural model means is that this whole thing is one computer. It's also one fault domain. It's also one trust domain. It means that any time a bug or an attack occurs in one of these computers, it has access to read and write all of the disk space behind it. Right? So not only can it damage the data that it owns, it can damage the data that anybody else owns, and it can damage the metadata that allows access to all of it. So this as a solution doesn't scale. You want to put more clusters in, different types of platforms, new machines. You will be increasing this risk of damage as time goes on, so it doesn't scale. It's fine for performance, but it's not a good solution. So there's a couple of us that are doing object storage, and I'll now talk about why this helps us solve this problem. So the Network Attached Secure Disk project is started in 1995, and in 1996 I went to the storage industry and I said, I'm talking about a storage interface. If you guys don't end up building this, it's not going to have much impact. It's not clear it's going to be really worth it. So I started this industry standards research group, and it started absorbing the CMU research. And at the end of the CMU project, it dumped it back out into a document that went into the T10 and the SNIA standards process. key idea, we want to move from a memory abstraction for disks, read block, write block, where you can't differentiate whether the data in this sector is, the relationship between the data in this sector and the data in another sector is unknown. You don't even know if there is any data in that sector. It could be deleted from the point of view of the file system. To an object model which says that I have an object ID, I have a bunch of data in it, I can see the relationship between the data in there, like think of that as a file. I can't see the metadata, I can't see free space. That gives me fine-grained access control. Fine-grained access control solves that problem with the Fibre channel storage, because I only give a client access to one file at a time. They never have access to the metadata under any circumstances, and they don't have access to anybody else's data. So if there is a bug there, they can damage their own file, which they could anyway, because once you have credentials to access a file, you can put anything you want in there. If you've got a bug in there, you trash your own data file. What else? We did this through the industry standards process. That means it's slow. So I started this in '96. It was standardized last September 2004. Okay? Takes time. One of the things that we did additionally was we said, you know, the closest analogy to this interface change inside the code stack for like Unix right now is the inode layer. The inode layer is below the cache. It's after you get out of the cache and you want to access something, you say, go get me the contents from the data in this file. There's a table of inodes. So you indirect into one of those tables, and that's where you find all the pointers to the data. But you also find some attributes. Things like the size of the file, the last time it was written. So we said the right interface here is modeled after the inode. So not only is it the data, but it should be some attributes. And of course, we put an extensible amount of attributes, because we didn't know which ones we needed, so let's put a million. And this allows the file system to put data in there, and ultimately it allows applications to put data in the attributes, which becomes a language for higher level applications to ask the disk subsystem to do something, whether it is a guaranteed bandwidth. Panasas, the company I'm going to talk about in a little bit, actually uses it to tag data with a RAID level and offer different redundancy levels on a file-by-file basis. All right, so CMU started in '95, built this standards body and SICNASD in parallel. When the CMU project stopped giving it new data, they decided it was time to chunk something out. They handed it off to SNIA T10. A little bit of politics. T10 is a true standards body, which means that nobody but the nerds that have been going for the last 30 years go to those meetings. You can't rally any political force around something like that. So you have a parallel marketing body where people who want to sell next year's products get together and try to argue why that standard you're building helps you with next year's products. Those things go together to create the political basis for paying for the standardization process and agreeing to it, and the technical basis for pinning it down. That thing went to standard in last September. Now, spinning out of these two projects were two different things. Panasas was a VC-funded standard company to try and deliver that technology by making it run well. Luster was an open source project to take the same abstractions and deliver it to people through the open source path. And they're both in good shape. Panasas, I will talk a little bit more about, is selling into large numbers of sites. Luster is providing the source code that HP uses in its product called SFS, so they're both available to customers. And in fact, the same people funded both of us, because nobody wants just one solution. They all want two or more. All right, so let's talk about how that works. An object storage device. How am I doing on time? Okay. An object storage device should be a disk. Object storage is the 11th SCSI command set. So it should be a physical disk. That's a Seagate disk, which means that the protocol should be in the ASIC and the microprocessor. But that's a big investment. That's not $1 billion to add a new disk line, but it's a lot of money. So in order to do this, you need the market for it. Well, if you go to Veritas and you say, build me a file system for these disks, Veritas will say, show me a market show me the disks available that I can ship right now that are cheap. Well, they don't exist yet because you're looking for the market. So it's a vicious circle, and it isn't going anywhere. All right? So you can't start that way. That's where you want to get, but you can't start that way. On the other hand, if you go over to this end and you take a great big disk array, you can afford to drop in front of it a PC, because the price overhead of the PC on top of the disk array isn't that big. Now it's a PC, so it can have a gigabyte of memory in there, and it can have a fast processor, and you can put together a relatively sloppy program to parse that command processing, and you can get the equivalent of one new command processor by building 40 disks and a big PC. So that's what almost all of us who first did it did. All right? So you get to start playing around with the protocol. You just have to do it at a gross level, not a fine-grained level, and not really delivering the price effectiveness. That's okay. This is what Lustre has done and is still shipping in a lot of products. What Panasas did was to say, I don't want to get caught there, because I have to end up here. So I'm going to try and do the best of both worlds. I'm going to build a little PC that has 2 serial ATA disks in it and a processor in it. Has a standard processor, has a standard PC. So the ease of programming can be done that way. But because it's only a couple of disks, the failure modes are a lot like this. What do I mean by that? This thing is a single spindle. If it fails, it has no internal redundancy. This thing is a disk array. If it fails, it has a RAID controller. It has internal redundancy. So when you're over here, you get to start off by ignoring the RAID problem. And that's what most of that industry has done. In here, with only 2 disks, it'd be pretty expensive to ignore the RAID problem. So we didn't. We treated the failure domain here just like this case. Meanwhile, the progress by Lustre and ourselves has led Seagate to go off and prototype a real disk with ASIC support for the protocol. It's not yet a product, but it's close. All right, so this is looking good for providing the goal of getting it down into individual disks. So then you take some kind of a metadata manager, some number of storage devices, put them together in a package, put scalable networking in it, and you have object storage. Panasas, for example, ships it in this 4U box. There are lots of choices. This one looked to us to be a reasonable trade-off. The way this is built is it's a blade server, has 11 blade slots. Each one of those slots plugs into a passive midplane. The passive midplane routes ether and routes power. In behind the passive midplane, we have dual power supplies, triplicated fans, battery, and dual gigabit ether switches. The gig ether switches are really cable management. They're not so much about switching, because 11 slots in here is 11 gigabit ether ports on one side, and then we have double NICs, so it's 22 really. And 22 cables coming out of the back of each one of these boxes is awkward for the user. So what you do is drive it into a switch. Now what you have is as many links coming out the other side as the sustained bandwidth you expect. These disks down here, the serial AT disks, when they're in use, we expect about 20 megabytes per second out of each one of them, which means I get 400 megabytes per second out of the shelf, 3.2 gigabits a second, so I take 4 links and trunk them together to make them look like one, and I get approximately the aspect of a single 4 gigabit per second link. All right, so these guys, this is just a PC, couple of, in this case it has about 512 megabytes of memory. It has a 1.1 gigahertz Celeron. I used to have an 850 megahertz box, but the 1.1 gigahertz is cheaper than the 850 megahertz. The reason that I will have faster processors in here is because Intel wants to stop shipping the slower ones. And really what I have to do is go to the microcontroller model, which can be a core, like a MIPS core dropped onto the back of an ASIC, arbitrarily slow, just whatever I need. Over here, on the other hand, we have more resources. Part of that reason is because of other functionality in here, but this is a 2.4 gigahertz processor with a single disk for the boot image, and up to 4 gigabytes of memory, and I'll talk about why. Okay, so there should be a problem here, because I was after bandwidth in the beginning. But I just gave you a new interface for a single disk. A single disk has one arm. It can move at maybe 500 megabits per second when it's in the sector, really sustains about 20 megabytes a second. That's not scalable. So to make it scalable, I have to bind multiple of these together. I also argued that I have to do RAID at that object level to get the fault model right. So I have to bind them together. So this is how I do it. A file is a collection of data and some attributes. What we do is we use a simple arithmetic map. We say that there are let's say, 10 object storage devices out here. There is an object on each one of them associated with this file. The file is organized in a stripe unit, 64K. The first 64K goes to the first 64K of the first object. The second 64K maps to the first 64K of the second object. The third 64K maps to the first 64K of the third object, and you wrap. Right? Now, the interesting thing about this is that, in fact, down here, inside the storage device, there is a table of pointers on where everything is, because at the bottom you need to be able to put them in arbitrary places. In existing file system, that table is the metadata, right? And that's what's in the inode. That's big. What we've done in here by using arithmetic instead of a table is we've squeezed down this mapping that we're actually shipping around the system to something very small. And the part that's very big never comes out of the box. So we have added a layer on the metadata mapping and got a big compression. That's a simple way to view what we've done with this arithmetic mapping. So the stripe size is one of the parameters. Turns out I put the RAID level in. Now, how does this work? See, RAID is normally done on sectors. I've just shown you a striping in the file. Right? So if I make sure that this column here is assigned to a different fault domain than this column here, then I have what I talked about before. I have independent fault domains, so I can calculate RAID across this abstract thing called a file and build RAID on top of the files. Not on the storage, on top of the files. Right? And these things down here don't know anything about it, but if there is a failed device, I enumerate its objects, which is enumerating the files touching it. Then for each one of those, I'm missing a piece. I just simply have to read the rest of the stripe, which has to be in different fault domains so I can successfully do it, compute the XOR, and write back the new thing. Right? So we moved RAID up to the information domain. So this is the it does deliver bandwidth slide. So in the lab, I put together 300 of these storage devices. That's 30 shelves. That's 3 racks. Not that much, but fairly expensive to have in the lab. And it's delivering 10 gigabytes a second. Which is roughly appropriate for a supercomputing cluster. Right? Until I did this, at the time I did this, the fastest known single file system was ASCII-Q at Los Alamos. It was running 18 gigabytes a second. So my lab configuration here was half of the fastest known file system. Right? We now have numbers significantly higher than that. So does Lustre. This is what Los Alamos built, that first generation. Down here they had 1,400 nodes from Linux networks, each a dual Opteron, 2,800 processors. Okay? They're now, I think they're up to 2,500 nodes. And we put initially 12 shelves down, 60 terabytes. They have doubled that, then doubled that again to 240 terabytes on this machine. And that gives them about 12 gigabytes per second of bandwidth available down here. So this box, which, by the way, I believe is about to start executing an 18-month job. And that's what that box is, that room, that acre of equipment is going to do. And once an hour, it's going to dump memory to that storage. Okay. Now, so what we've done here is we've developed a new interface for storage. All right? Now, a new interface means a new protocol leaving the wires. But you remember early on, I want those wires to go straight into the clients, which means there's a new protocol going into the back of the clients. Well, that means there's some change in the code in those clients. What we did was there's a wonderful interface for doing this. It's called the Installable File System interface. We drop in an installable file system into these clients. And we, in fact, do this for Linux, about 40 variants of Linux, which, by the way, don't let anyone fool you that there's one Linux. The current number, this one is a useful number, 1.3 Linuxes per customer. Scaling linearly. It should level off, but I haven't seen it. Yeah. So we put an installable file system. What this does is it goes to the metadata servers when it wants to get access to a file. That goes through a credential check, gives you back a map. Now the individual devices can go direct. That's where all the bandwidth comes from. Unfortunately, not everybody wants new software in their machines. First of all, I don't want to support all the platforms out there. And second of all, there are machines you just do not want to mess with, typically desktop machines. Therefore, and everybody wants access to their data from all possible machines. Therefore, what I'm going to do is I'm going to put NFS and CIFS servers in here that access the same data at the same time consistently, and that any other machine can get in through these guys. Right? I also want to make sure that this scales, because I can't have a bottleneck there either. So all of our director blades, who are all just about doing this access correcting checking, actually run NFS and CIFS servers as well in order to access the same data. How do they do this? Slightly differently than the forwarding mechanism. Now a client using NFS and CIFS has to bind to a single point, right? A single server. So pick one. The difference is that our NFS and CIFS servers are built on our own file system, our installable file system. And that installable file system, if it needs metadata, goes to the metadata server, gets the metadata, and then goes directly in the back end. All right? So the difference is we're going to copy data in the NFS land through just one server, not through two. And we're striping the data over all the storage in the back end, so the individual files can get larger, the volumes can get larger, and they can scale in bandwidth as well. There's been really virtually no penalty for this impact in the benchmarks that we've been using. So this is a better way to do scalable NFS. So I already showed you the 10 gigabytes per second for 300 object storage devices scaling. Well, just for comparison, a standard NFS server, high-quality NFS server, is probably going to give you a half a gigabyte a second. If you're lucky, a few hundred megabytes a second. Now, I was out for bandwidth. You might assume that in building something that does bandwidth well, I sacrificed everything else. So what we did is we want to make sure that wasn't the case. So we went over here to the NFS benchmark of choice, spec SFS. We said, all right, let's compare ourselves to standard NFS servers of the same total capacity, number of spindles. The basic, most of the cost in an NFS server will be in the number of spindles in the bottom. So roughly 90 in these two systems. And the main point I want to make here is that these numbers are roughly comparable. I'm not paying any price in the standard benchmark that is used for standard file systems for doing everything based on objects. And then it's scalable, so it scales up to big numbers. In fact, we were doing a competition for a potential customer in New Zealand who has something to do with, mythical figures from J.R.R. Tolkien. And their benchmark was an rsync. An rsync is a walk of the entire tree looking at the attributes. No data motion, no bandwidth requirements at all. It's just visiting everything. And that thing was chugging along for hours at 300,000 NFS ops per second. So, these type of scalable performance metrics will matter for more than just bandwidth. Twice as fast as the competitors. Now, I want to go way back to the notion of the reliability curve and that equation. It said the mean time to data loss was inversely proportional to the reconstruction rate, the repair time. By moving RAID to the information level and spreading the information over all the resources, I can use every computer and every spindle in the reconstruction. That's not what happens in RAID today. You got a stack of RAID boxes. This particular RAID does all the work for a failure recovery in that particular RAID, and all the others are unaffected. Right? By spreading it out, what I can do is put more resources to bear. I can read in parallel, I can write in parallel, and I can XOR in parallel. So instead of 10 to 15 megabytes per second reconstruction bandwidth, which you can get in a standard RAID today, as the system gets bigger, the RAID bandwidth gets bigger. So the reconstruction time, let's say this is 12 shells, we were doing about 100 megabytes per second for reasonably big files. It's a different ratio for smaller files. But the whole point here is that I can get an order of magnitude more bandwidth, which cuts the reconstruction time by an order of magnitude, which shortens the window of vulnerability to double loss, which protects against the loss of data in the RAID. Effectively, all of that is to allow me to build bigger systems. And if I build bigger systems, there are more faults. I have to do something in protection. Not only can I do stronger encoding, I can repair faster. Okay, last little story. So the problem at this point is that if we replace, so this is the SAN file system, if we replace with these installable file systems to get access to the back ends, whether it's the solution I have or somebody else's solution, then there is vendor-unique file systems in here. Vendor-unique file systems are scalable, high performance, but the engineering costs of maintaining them supported by one company. There isn't second sourcing, so that if you go with one, you get stuck behind them. There isn't competitive pricing structures because it's hard to compete. So the customers basically don't want to do this unless they have to, which means that the scalable file systems and cluster file systems have only been able to fill the need of customers that had no choice but to go look for them. Everybody else is going to stick with NFS because NFS is familiar, reliable, cost competitive, many sources, right? So basically, that's not good. So what I'm involved in now is an effort to move the advantages of those cluster file systems into the NFS infrastructure. We'll call it PNFS extensions to NFS v4. So this is just a picture of a birds of a feather that happened last April of 4. Group of companies and universities working on this got together and said, let's add just the map. Remember that funny little picture with the striping? That's the map. Just add that map concept that a client asks the NFS server for access to data, and instead of getting back the data, they get back a map. Then they can reach directly through the storage protocols to the underlying storage protocols. And let's do it for all the storage protocols. This thing is making progress. We are deep in the process of specifying how to do that for NFS v4. Basic architecture, where you would have an NFS file system in the client, we'll put in a disk driver notion. And this disk driver is the thing that understands a specific map and can access a protocol on the back end. And then a new NFS server should respond to these requests that say, get me a layout by reaching into the local file system, finding out where things are, locking that positioning, passing the map of where things are back to the client, which can then access directly. Right? And then whenever the underlying file system wants to change the layout of things, they revoke that map. Once the map is got back from the client, they can change it. And we'll do this for files, objects, and blocks. That's the other order. Why? Well, 90%, 95% of the market out there that's high-performance SAN file systems is based on blocks. So let's bring them along. Files haven't got any solution out there and want a solution. So and besides, they're the guys that control the NFS v4 world. So we'll bring them along. And the object solutions that the Lustre people and ourselves are doing fit into this model. So this is the vehicle for bringing the capability of that parallel transfer that I've been working on since I started in RAID to you in the form of NFS. It's kind of like that. The technology is going to change, but the name's going to stay NFS. All right? And I'm done. Any questions? Sure.
Where does the Google file system fit in your taxonomy?
Google file system is interesting. There's another one like it, PVFS. It's an application middleware solution. So the storage is on the individual nodes. It's local file system. And the application binds in a library and then asks the library to fetch data. And the library opens up local disk files in ext3 or whatever it is and pulls the data up, which means that it doesn't normally fit into the standard definitions of a file system. It's not something that you run LS on, because when you run LS, you see the components, right? But it is an object model in the sense that files are decomposed into pieces on different servers, and they have a metadata layer that's going to point to the pieces, and then they're going to fetch the components. And in fact, one of the principal designers of the Google file system is Howard Gobioff. He's the one who did the dissertation on the security for our system working in the NASD project before. So it could be called a block or an object file system, but it probably shouldn't be called a file system in the sense that it doesn't work for all apps. PVFS fits in that same category.
So does this mean that StorageNet, or it was whoever's making that prototype disk,
Seagate.
Seagate. If Seagate put their disk, does that mean it's going to have a gig E interface on the back?
No. Well, so I'll be scrupulously correct here. Object Storage Devices, OSD, is the 11th command set for SCSI. SCSI has an architectural model that command sets fitting into transports. There are multiple SCSI transports. There's serial attached SCSI, there's iSCSI, there's Fibre channel. It has to work in all of them to be a SCSI command set.
So the part that's moving it onto the disk then is simply this extra intelligence of treating the disk as objects instead of treating it as blocks.
Yes.
We would say anything about quality of service, and I'm wondering whether that's an issue that you think is significant among your customers care about that.
For storage, quality of service is not that often about bandwidth. It's an awful lot about something they're calling ILM for information lifecycle management. What you can think about ILM is a rebranding of HSM, the hierarchical storage management. It's about putting the data on the appropriate storage. So you've got fast, expensive storage, you've got slower, inexpensive storage, and you want to brand the data with attributes or some kind of an algorithm to decide where to put it. Should it be mirrored? Should it be replicated? Should it have 3 copies? Should it be put out to the other side of the world? Quality of storage is an awful lot about those things. So you want to tag something with enough information about the information. Ideally, you want to say mean time to data loss for this data and determine the reliability for it that way. You want to determine things like whether or not it is better to lose a little bit of data at a failure or to come back up quickly. So there's a giant trade-off in replication technologies between how much risk you take and how quickly you come back up. You want to put that kind of information tagged on the data so it can be manipulated by the system. Really, the reason is that the capital outlay for storage is 20% of the total cost of storage. The other 80% of the total cost of storage is split between the operational costs of integrating in new systems, configuring new systems, reconfiguring them, load balancing them, backing them up, and losing revenue when it's unavailable. They all turn out to be quality of storage issues. Okay?
In using off-the-shelf, expensive off-the-shelf components, are you worried that sometimes you're sort of operating on reactive mode, that it almost seems as if you're waiting for the entertainment tastes of 14 to 25-year-old males to provide the technology that they can leverage? Isn't that the tail wagging the dog?
Yes, and that's the fiscally responsible position right now, is to say that if you want to build cars, you need to build them out of the parts that are manufactured in high volume with some level of reliability and control, because if you go and start banging metal by yourself, you won't be able to control quality or cost. And so, the short answer is we try to influence the ALU designs, but the amount of money that is spent for high-quality scientific computing is tiny compared to the amount of money that is spent for rendering, Doom faster on the screen. Okay? It was invented to be a unique word that sounded a little Greek and a little bright, and it wasn't intended to mean anything at all. But in fact, my wife did put a translation on it. It was the Pittsburgh Advanced Network Attached Storage Appliance Software. Okay?
I have the privilege of thanking Garth for talking. Before I do that, just a couple of announcements. You want to talk to Garth some more? There's a reception here in DC 1301, actually known as the Fishbowl, which is just right behind us. The second announcement concerns the fact that this talks a family affair, I gather. Your father and 3 brothers are here. I'm told they came to finally find out what you do. All still don't know. But there's a quiz at the reception, so you have to answer a couple of questions. I also like your symbol. It's sort of infinity going on the angle. The sky's the limit or something.
We call it the Infinipy.
Very good. As a member of the committee that chooses the recipient of the Graham Medal each year, I'm delighted at our choice this year. I don't know if I ever ran into Garth when he was an undergraduate. Since I've been around here forever, I probably did. But Garth, you fit very much within the model that we're looking for. First of all, you're very excited about what you're doing, that's for sure. It's innovative. And there's something in it that seems to be somewhat entrepreneurial, too. So that fits exactly the model that we had in mind. I was reminded yesterday by one of my colleagues who retired that Wes Graham once said that being a professor is the next best thing to being financially independent. Well, you've achieved one goal, and it looks like you're well on the way to the second one. Again, thank you very, very much for a really interesting talk, and looking forward to
Thank you.
getting together with you in the fishbowl.
All right.